Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to give an example of how to work a related rate problem. So what we're looking at here basically is a model of a coffee maker. This is number 34 in the textbook I happen to be using for this calculus class right now. The top of this here is cone shaped, has the following dimensions: 6 inches wide, 6 inches tall. The bottom is cylindrical in shape here, the 6-inch diameter. Coffee is pouring here from the cone to the cylinder here at a rate of 10 cubic inches per minute. Got an extra M there I'm going to get rid of. All right, so what we're going to do here is we're going to try to calculate how fast the water level or coffee level is dropping here and how fast the coffee level is increasing here. So in the language of calculus, those are dH/dTs, where h is the height or depth of the coffee in each tank. So I'm going to go ahead and take the, let's take the cylinder first here. So this blue line is representing the water level or coffee level, and this shape is cylindrical. The volume of a cylinder is pi r squared times the height, and the height is what I'm calling h. We know that the volume of this is increasing at 10 cubic inches per minute given in the problem. We're looking for how fast h is increasing. And what we can do now is take the time derivative of this entire equation here. Right, so again, you can think of the derivative as an operator. So what we're doing is differentiating both sides of the equation. So the derivative of the left-hand side is dv dt equals. Now, pi is a fixed numerical constant. Right? We look at this r term and we have to ask ourselves, is r changing? If the answer is yes, you need to use the product rule on that. If the answer is no, you can treat it like a constant. So I look at my problem and I imagine here as this h moves up, as the coffee depth gets higher and higher and higher, the radius is 6 inches, 6 inches, 6 inches. I'm sorry, the radius would actually be 3 inches. That 6 inches was the diameter. But the important point is it's not changing. So as far as this part of the problem is concerned, dr dt is 0. Or in other words, you can just treat r like a constant. So I'm going to go ahead and do that. Treating r like a constant, this is going to read pi r squared. However, h is changing, so it has a derivative, dH dt. That we'll calculate here in a moment. Now putting in numerical values, dV dt in this problem is 10 cubic inches per minute. Let me go back there and redo that a little bit. 10 cubic inches per minute equals. Now, as far as this geometry is concerned, that is a positive dV dt because the volume of the coffee in the cylindrical part of the tank is increasing. Pi times the radius is 3 inches, and that's being squared, times dH dt. So it's pretty easy to solve this for dH dt. We're going to get 10 cubic inches per minute divided by pi times, I'm going to go ahead and just take this 3 inches squared and write that 9 inches squared, 9 square inches. So again, this is 9 square inches, 10, and then we would be dividing by that to solve for dH dt. Now, dimensionally, these square inches and these cubic inches are going to cancel. This is going to give me some numerical value that I'm sure we'll have in a minute. And then unit-wise, we end up with inches per minute. And I'm going to ask one of my helpers here to grab a calculator and give me 10 over 9 pi. Should be right around 0.3, I'm thinking, as this product is right around 30. What do we get? Yeah. Should be. You need to make sure you use parentheses here. This bottom is right around 30. 10 over 30 is around 0.3. So somebody give me 10 divided by, when you put this in your calculator, put brackets around that. 0.35, great. So about 0.35 inches per minute. That's how fast this height's moving up. All right, now we're going to work on this volume. I'm going to draw this in blue here. We're going to work on the volume in here, and we're going to look for how fast the depth, the water depth here is changing. I'm going to go ahead and get rid of some of this other work that I did. Whoops, not what I wanted to do. Didn't mean to get rid of all of it, just this stuff here. We don't really need this. And again, now we're going to focus on this. Now, I'm going to go ahead and actually put a little coordinate system here. Whoops, except I'm going to do so in a different color. All right, X, Y. Now, here we have a cone. The volume here is cone-shaped. The volume of a cone, I believe, is 1/3 pi r squared h. I'm going to take a moment here and just pause this and just verify that, make sure, because my memory is not as good as it should be. We're verified. Again, I don't like to trust my memory on stuff. So the h here in this question is going to be this height right here, the water depth. And the volume is referring, though, only to the volume of the coffee. So that's just the stuff here I've got kind of shaded in blue. Our problem, it's not a huge problem, but the thing we have to consider is this. That's the radius of that cone. And as the water or the coffee comes out of the cone, both R and H are changing. That makes this a two-variable problem. So what I want to do here is, because this is a single variable course, is get this reduced down to one variable before we do anything. If we time differentiate as it sits, we can, but this is going to have two terms. It's going to have, the first derivative is going to be 2r dr dt times h, plus the next term is going to be r squared dh dt. So to get this down to one variable here, we want to eliminate one of these variables. And that's why I put this coordinate system in here. If I focus kind of on this line right here, and I think of that point as a point in this coordinate system, that would be the point 3, 6. Because it's 6 units across, so from the center it'd be 3 units over, and it's 6 units high. That makes the equation for this line y equals 2x. Because all lines can be written in the form y equals mx plus b. The m is the slope, 6 over 3. Or you could think of it as 6 minus 0 over 3 minus 0. And the b is 0 just by observation. That's the intercept of that line. Now, getting back in terms of like h and r, the y is the h basically, and the r is the x. So the relationship between r and h is h equals 2r. Because what we're looking for is dh dt, we want to eliminate r. So r is equal to h over 2. And I'm going to go ahead and rewrite this equation. Let's see, pi over 3 times r, which can be written h over 2 squared, and again times h. And now I'm going to just separate off the constants here. So pi over 3, and this is 2 squared, so this is 4 times 3 is 12. So it looks like pi over 12 times h. There's 2 of them here and 1 more there, cubed. So there's that same formula as a function of h. Now I can calculate dv dt is going to equal 3 pi over 12 times h squared dh dt. All right, and that's from differentiation of h squared. Bring down the 3, subtract 1. Keep in mind that h is time dependent. It's changing. That's why we need the dh dt, because that's the chain rule of differentiation. And I think these are all values we have. So I'm just going to go ahead as this equation sits and put in the values right now. So dv dt, right, is 10 cubic inches per minute. However, I'm going to take note that as far as the cone is concerned, that's a loss in volume. So I'm going to use minus 10 cubic inches per minute as the rate at which this part is changing in volume, equals, let's see, 3 pi over 12. How about we just write that pi over 4? Pi over 4 times h squared, the h is 5 inches given in the problem, times dh dt. So now we can solve that for dh dt just by taking this negative 10 cubic inches per minute and dividing by this product. I'm going to take a moment here while one of my helpers here does that calculation. Somebody grab a calculator here and run that, and I'll just pause it while we wait. So back here, and we're looking at about, when we solve this for dH/dt, it's looking like it comes out to be about minus 0.51 units, work out to be inches per minute. You'll notice there's inches cubed here and inches squared here, so these will kill the inches squared, leave you just inches over minutes. It's negative because the depth of the coffee is dropping. So the point of this video is how to work a related rate problem. There's actually two little problems here. The cylinder problem and the cone problem. The cone problem ended up being a little bit more complex because here the radius was a function of the depth. As the depth dropping, so is the radius. So a function had to be found between the radius and the height. Right? In the bottom problem, the radius was not changing. As this goes up a little higher, the radius is still 3 inches. A little higher, the radius is still 3 inches, and so forth. So anyway, I hope this video helps demonstrate how to work these related rate problems. Have a great day.